We will now see how pressure, being a function of depth, leads to a force that acts on objects in a fluid that are either completely or partially submerged. Consider the following figure where a cylindrical object of height h is being held under the surface of a liquid. The pressure P1 at the top of the cylinder produces a downward force on the cylinder equal to P1 times A, where A is the cross-sectional area of the cylinder. Likewise, the pressure P2 at the bottom of the cylinder produces an upward force on the cylinder equal to P2 times A. However, since the pressure is greater at greater depths, P2 will be greater than P1 by an amount equal to rho GH. Therefore, there will be a net upward force on the object equal to P2A minus P1A. This force is known as the buoyant force, and it will be applied to an object immersed in any fluid. From the equation above, we see that the buoyant force is equal to rho GH times A. The product of H times A is the volume of the fluid displaced by the submerged object, and the density rho denotes the density of the fluid, not the object. Therefore, the product rho HA is equal to the mass of the displaced fluid, and the buoyant force is equal to this mass times g, which is just the weight of the displaced fluid. This result was discovered by the ancient Greek scientist Archimedes. When applying Archimedes' principle, the shape of the object is not important. No matter the object's shape, an upward buoyant force will be applied to the object. The buoyant force is not a new type of force. It is just the name given to the net upward force on an object exerted by a fluid. Let's now explicitly state Archimedes' principle. Any fluid applies a buoyant force to an object that is partially or completely immersed in it. The magnitude of the buoyant force equals the weight of the fluid that the object displaces. From a problem-solving standpoint, if an object is immersed in a fluid, then you should include the upward buoyant force in the free body diagram for the object. The overall effect of the buoyant force will then depend on its magnitude compared to the magnitude and direction of the other forces acting on an object. For example, as an object is placed in a fluid, there will initially be just two forces acting on the object's weight and the buoyant force from the fluid. As more of the object's volume becomes immersed in the fluid, the more fluid it displaces. This increases the buoyant force acting on the object, which is equal to the weight of the displaced fluid. At some point, for many objects that continue to displace more fluid, the buoyant force on the object becomes equal and opposite to the object's weight. At this point, the object will float. This may occur even though only part of the object is submerged. However, many other objects will never float, even though they are completely submerged, and thereby maximizing the buoyant force acting on the object. These objects would sink to the bottom of the container, but the buoyant force still acts on the object even though it's not large enough to balance the weight. For an object that sinks, the buoyant force will reduce the normal force acting on the object from the bottom of the container. Let's look at the condition for floating. The buoyant force must equal the weight of the object. But by Archimedes' principle, we can write the buoyant force as the weight of the displaced fluid. Each of these weights is equal to an mg. The g's cancel, and we see that the mass of the displaced fluid, being equal to the mass of the object, is another necessary condition for floating. Each of these masses can be written as a density times a volume. The maximum buoyant force would occur when the volume of the displaced fluid is equal to the volume of the object, i.e. the object is completely submerged. This shows that the condition to float requires the density of the object to be equal to the density of the fluid. This applies to the case of an object that is solid throughout. If the density of a solid object is greater than the density of the fluid, it will sink. Likewise, if the density of a solid object is less than the density of the fluid, the object will float. Ice cubes floating in water are an example of this latter case. Water has a density of 1,000 kilograms per cubic meter, and ice has a density of 917 kilograms per cubic meter. However, it must be possible for objects with densities greater than the fluid they are immersed in to still float. Steel ships, for example, can float just fine in water, even though the density of steel is almost 8 times the density of water. The key is that the steel ship is not a solid piece of steel. The steel in the ship is shaped like a large bowl, so that it displaces a much larger volume of water than would the same mass of solid steel. By displacing more water with its shape, the buoyant force on the steel ship is greatly increased. So much so, in fact, the buoyant force can now be made equal to the weight of the ship so that it floats.